everybody. My name is Deepanshu, and I'm a Vice President of Flash Memory Technology at Western Digital, which soon will be called SanDisk, and I'll explain the story. So just wait a sec. So the title of the talk is NAND Flash Memory and how we have been innovating, or the whole industry has been innovating, to keep up with the world's storage needs. And we'll talk about what that means. Let's dive into it. So, you might have a hard day sometimes. College life is difficult. And sometimes you're like, I had a hard day. My girlfriend dumped me, or or maybe I had a bad grade. My professor gave me a bad grade, or I messed up something. And you'll go home and you're like a little bit sad. So sometimes to cheer you up, you'll like watch some funny videos, go to YouTube or something. Maybe one of them could be cat videos. It's typically a funny videos. And you would think that, oh, how cute this cat is. And so many cat videos around. And you're like, how can humanity survive all these so cute cat videos? I can't stand it. That's the problem that you all might think about. But in our job, that's not what we think about. What we think about is how are we going to store all these cat videos? That's the business we are in. We are in the storage business. So we store data that all of you produce. Okay? That's what Western Digital does. So what is Western Digital? So data is stored today in the current world in two different types of storage technologies. One is hard disk drive. By the time most of you were born, in laptops, there is no hard disk drive anymore. But believe it or not, 20 years ago, or maybe 25 years ago, there used to be hard disk in laptop drives. Okay? So that is one storage medium, hard disk drive, HDD as it's called. The other storage medium is flash memory, which is how most of the laptop storage is based today, solid-state drives. So, but hard disk drive, HDD, is still very popular in the data center. So when you take a picture or something and it goes into the cloud, that cloud, how is that data stored? It's more than 80% of it is in hard disk drive. So in totality, if you look at the total amount of bits stored in the world, whether it's in the cloud or in your laptop or in your phone, if you look at our totality of that, 40% of the bits that are stored in the world are stored in a WD device. Where either it could be a HDD device, which could be on the cloud most likely, or it could be a flash memory device, which will be in your pocket or will be in your laptop. So that's how big the Western Digital presence is in the data storage market. And the products that you see typically in the market would be WD Black. If any of you are gamers, I'm sure many of you are. WD Black is a popular SSD. All right, I got one customer. So then if you're in camera, digital camera, there's Extreme Pro cards which are going to the camera, digital cameras. Then you have USB drives, and of course you have the memory chip going into your phone. So in gaming area, cameras, PC, clouds, phones, automotive, IoT, it's all based on flash memory. And data center is mostly running on hard disk drive. So these are the brands with which WD products are marketed with. SanDisk brand, which is in the consumer market. SanDisk Professional, which is the upper end of that. And then WD in hard disk, and WD Black in the gaming segment. So like I said, 40% of bits produced in the world are stored in a WD device. That's how big the WD footprint is. It has about 50K employees spread across 11 countries, predominantly in US, Japan, India, and China. That's where majority of our presence is. We have some presence in Israel and some presence in Malaysia as well. So that's the introduction to Western Digital. Now, sustainability obviously is a super important thing. Should be for everybody, but definitely in the youth, people, all of you, I'm sure all of you are very environmentally conscious, and so is Western Digital. So sustainability is a top priority for us, for our corporate board. So we come up with a sustainability report every year. This was back in 2023. We have set some aggressive goals, I would say. By 2023, we want to be carbon neutral, net zero. And by 2030, we want to have 42% reduction in our manufacturing sites. Similarly, in renewable energy, by 2030, we want to have 100% renewable energy usage in all our businesses. For water consumption, we want to reduce it by 20% by 2030. And for waste, the things that go into the landfill, only 5% of the things we produce will go into the landfill. These are the goals that the company has set forward to, and we're on track to meet these goals. In addition to this, apart from how we manufacture NAND, just the way the technology progresses from one generation to another, it becomes more and more energy efficient. So there are two ways we are tackling sustainability issue. One is how we manufacture the memory, This is where these goals are. The other is how the technology of the generations we are coming, one generation or another, how power efficient these technologies are. Every generation is becoming more than 15% more power efficient. So 2 ways we are trying to solve the world's sustainability problem from energy consumption point of view. There are many Purdue grads in WD. So this is just to name a few which work in the area where I work in, memory technology development. We have, some of you might know these professors. So these are just 5 recent students who have been, not recent students, but people who are in our group who work in the flash memory technology area. And I hope one of you is going to join, some of you are going to join WD soon as well. Now, oh, I think I missed one slide. Sorry, before, should have talked about this. So I want to talk about my personal journey as well before I dive deeper into the technical topics. So I was born in India, in New Delhi in 1983. Not as young as you, but still pretty young. I did my undergraduate in IIT Delhi in 2001 in engineering physics. Then I did my master's in material science and engineering in UC Irvine. And then right after that, in a year, I finished my master's in a year. And because my aim was to just start working in the chip industry. And I started to work at SanDisk in 2006. And then 2016, SanDisk was acquired by Western Digital, which is where we work today. But what's happening now is the history repeating itself. So we're kind of going back in time. The Western Digital is going to split it into 2 companies called Western Digital, and guess what? SanDisk. So 2 companies. SanDisk is going to be the flash memory maker of the company. Like I said, Western Digital today has hard disk drive and flash memory. The flash memory piece of it is going to go into the company called SanDisk. And then the hard disk piece is going to remain with Western Digital. So we're going to become 2 public companies at the end of this month. Almost we're in the middle of the split. And the only thing that has changed is the logo. The logo looks slightly different, kind of similar, but slightly different. The way the SanDisk is written is different. But other than that, most of the things that the company works on is pretty much the same. So we're kind of going back in time. And this is my family. This is me, my son, my wife, Bridget, my daughter, Sitara, making a funny face. And we cannot miss our 2 dogs. These are my 2 pets we have. So this is my personal journey. And I think one thing I would say about my own personal journey is that many of the things that happened in my career were not anticipated, right? So it's very hard to be precise about where you will land 20 years from now. It's very difficult. You just need to have a broader view of the vague area you want to work in. What exactly you're going to work in that, you might think you know, but you don't really know. Okay, so I just know, okay, the SanDisk was a company that works in semiconductor chips. That's all I knew. And I knew that back in 2006 that chips is going to rule the world. Every device you look around you has chips in it. That was clear to me, that's the future. All I wanted to do was go into chips. That's it. I didn't know what was flash memory. I didn't know what was hard disk. I didn't know what was processor. I have no idea. All I wanted to work was in semiconductor chips. And SanDisk just happens to be one company that works in that. And I got into that, and what I started my career with was a different job, and what I'm doing now is a different job. I started as a test engineer. Now I'm leading a technology development department in the company. So I think one lesson from my life in this is that you don't need to be too precise into what you're going to do, but you do need to have some vision of where you want to be, broadly speaking. And just keep chasing that vision, and good things will happen to you as long as you're motivated, self-motivated to do it, and you truly believe in what you're trying to do. And the urge to keep on learning, the curiosity is unbeatable. Basically, your technical knowledge will only take you so far. What is more important than that is your soft skills, your life skills, your curious mind, and the ability to keep learning. That is much, much more important than anything you'll learn in this university, I'm telling you. Technical skills only take you this far. What differentiates good from great is not technical skills. It's the ability to work with people. It's the mindset of trying to do something better. That's what it takes. So that's something to keep in mind. Don't just focus on learning the next best technical things. Keep in mind of how to keep improving your learning skills, especially in the world of AI. You don't even know what you're learning right now will be relevant 5 years from now. But what's going to be relevant is the ability to keep learning. So that's a very important aspect of life that I would hope all of you take a lesson from. All right, now let's dive deep into the outline of the talk. So we're going to talk about data growth, that what is causing the demand of flash memory to go up. then how is flash memory satisfying that need, and then how did we actually do in terms of technology point of view, what changes did we make to satisfy this exponentially growing data growth, and finally, what's going to be future of flash memory as we look forward to. So data. I think this is well known. I mean, look around you. How many sensors, how many devices, how many things you have in your pocket, in your home, etc. Everywhere. This thing is collecting data. I bet there are sensors in this room, camera or something that's collecting data. That laptop there is collecting data. Every phone you have, everything I'm speaking, your phone is listening. This is all data collection happening, right? So data is getting created left and right across the board. And it's only going to go up and up and up, right? It doesn't have to be some big brother watching you, but data is useful in general, even for your own life, because a lot of analysis can be done through data to figure out what things need to be done out of it. So data has been growing, and why it is growing has been changing over time. So this is showing the data growth over time, and you can see exponential curve. And the area where the data growth is happening is changing. So originally it used to be more in the endpoint. Endpoint means devices like your phone, right? But now data is more residing into cloud. So where the data growth is coming from can change over time. And I'll talk about AI next, which is another source of data growth. But one thing is for sure, if human civilization is going to continue to grow, exponential data growth is inevitable. Because this is what drives civilization to get better and better. As civilizations get more sophisticated, data gets generated. This is a way to know whether human civilization is going in the right direction or not. If you're creating more data, you're getting more sophisticated as a species. Okay? So data growth is inevitable. You can mark my words on it. I cannot tell you 5 years from now what application will be driving data, but I can tell you data will be growing exponentially. Otherwise, human race is not going to basically survive long term if this growth ends. This growth is inevitable. So this data growth is happening, and then you have to find a way to store the data. And that's where the flash memory technology comes in. So now AI, right? 5 years ago, nobody was talking about all this, right? I mean, maybe some scientists in the computer engineering department was talking about it, but a random consumer on the street did not know about AI. But now AI is suddenly driving the data growth. So how is AI driving the data growth? So this is a simple machine learning neural network model, right? So what you have here is, this is how the basic neural network started, that trying to identify different pictures. So you have a picture of a dog, 2 different types of dog, cat, and horse. And then you train this model to say, you sort of label each picture. You say, okay, this one is a dog, this one is a horse, this one is a cat. And you describe the picture in as many metrics as you can. Okay, so a picture can be described as, hey, this pixel is white color, this pixel is brown color. That is a way to describe the picture. So in a way, you have to describe any entity in some metrics. And then you say what that entity is by labeling it. And then there's a neural network in between that will connect the relationships between them. Because even as a human, when you look at this picture, you know it's a horse. But how do you know it's a horse? A 1-year-old kid may not, maybe 1-year-old kid might know, but 1-month kid does not know it's a horse. How did you know instantly it's a horse? Because your brain has saved these things by your experience. You have learned through that by observing things. The same thing neural network does, right? So it connects the input that you're grasping with the output of the picture. And then you train this model, and then over time it builds these relationships, which is essentially a mathematical equation that connects the input to the output. And this is the neural network field. So what's happening, talking about in terms of data, is that the number of parameters or number of weights that describe this input to output connection. So this equation, the y1 equal to x1, which is the inputs, y1 is the output. The weights, which is the linear algebra of how many metrics are used to connect the input to output. These weights, as the neural network gets more and more sophisticated, those weights, the number of weights you need to describe a model is growing exponentially, actually super exponentially. This is that plot. This is showing parameters. Parameter means number of weights, number of W's that you have in this equation as a function of date. Okay? So you can see that the trend chart shows that it was up to the ChatGPT phenomena. It was doubling every 1.5 to 2 years. So still exponential growth, but not that fast. Guess what has happened since ChatGPT came along, the large language models came along? It is doubling every 3 to 5 months. So this is super duper fast of rate of growth of parameters. Now these parameters, these weights, are ultimately data. They're zeros and ones. This has to be stored somewhere. So what's happening is that there's a memory chip where these weights or parameters are stored, and there's a compute chip where these calculations happen. So as the number of parameters of each and every more sophisticated large language model is going up, the amount of memory chip you need to store those parameters also has to go up. So this is yet another example of a new application requiring more data. This is just a recent example. There will be more examples down the line 10 years from now that we cannot anticipate today. These things will keep changing. There's nothing unique about AI as far as data generation is concerned. There'll be more applications along the way. Just like digital pictures came along, video came along. These are just new applications that keep getting generated, which cause data to exponentially grow. AI is just another one in that long trend line, right? So, but this is the latest trend. So this AI is going to, the large language model getting bigger and bigger is going to drive the storage need of this memory chip to grow bigger and bigger. Because the calculations happen in the GPU, and all of you know which company makes that, NVIDIA. So, but the data is stored in memory chip, and data has to go back and forth for calculation between memory chip and the compute chip. So as the model size goes up, the memory storage required also goes up. So this is yet another example of data storage need going up. Now, so now we have sort of understood that data is constantly exponentially growing. Now the next question is how flash memory has been satisfying these data, the exponential growth in data. So let's understand what flash memory is before we talk about how it stores the data. So before you talk about flash memory, you have to look at the overall memory hierarchy. So like I said, there's a hard disk drive, which also WD makes. But that's just one type of memory. There are many types of memories. So hard disk drive is spot set at the bottom of the pyramid. We call this memory hierarchy pyramid. And then as you go up in this pyramid, the speed, performance at which you're reading the data, programming the data keeps on going up. But what goes down is the density. So the more you go on the top, the faster things become, but less dense they become. So at the bottom of the pyramid sits hard disk drive. It is super dense, so you can have 10 terabyte, 20 terabyte hard disk drive, but it is super slow. Its latency is 10 milliseconds. Latency means if I give a command to the memory, I say, hey, go do something. Go do something means go read the data, go program the data, go erase the data. How quickly the memory does that job. That's what latency means, right? So hard disk latency is a 10 millisecond regime, but it gives you super high density. As you go up, the NAND flash memory is the next one on the block. So that latency is 10 to about basically, 100x better. So that's 10 to 100 microsecond latency, but the density slightly reduces. And you keep going up, you have DRAM, SRAM, and then all the way to CPU registers, cache. So what is good about NAND flash versus DRAM is that NAND flash is a non-volatile storage. What does non-volatile mean? That means once you write data into it, and you plug it out, you take all the power out of it, the data can still survive. That's the meaning of non-volatility. That means data is not volatile, it can survive without power. So the green dot here refers to non-volatility. So DRAM is faster, but it requires constant power. So if you check your phone, right, if you are browsing something and you have some website open in it, you check your phone again, the website will open very quickly. Why? Because it's stored in the DRAM. But try to turn off your phone and then try to turn on, go to the same web page. It will open very slowly. Same thing with the picture. If you took some picture, you immediately look at the picture. It's very fast, you can see it. Switch off the phone and try to do it again. It will come back slow. So that's because the DRAM is storing that information, but while the phone is on, is powered on, its information is in DRAM. Once power goes away, DRAM loses that information, and that information now goes back into NAND or hard disk drive, depending on the product you're using. So that's the volatility of the memory. So what NAND flash memory does is that it sits in the sweet spot where it is not as slow as hard disk. It has other advantages like it is light, it's durable, but it is still non-volatile. That means it does not require power. This is the key advantage of NAND flash as compared to DRAM or hard disk. It sits in the sweet spot which is faster but still non-volatile and as compared to DRAM. That's the advantage of NAND flash as compared to hard disk or DRAM. So it's in a very sweet spot which satisfies most of the consumer needs. Now, if we look at how I showed the previous plot showing exponential data growth happening. Now, this is the plot showing how the NAND industry bits have been increasing to keep up with that data growth happening. So this is showing the total amount of bits that the NAND industry has been shipping over the years. This is plot in log scale. So linear line in this is basically exponential growth. So you can see that the total bits the NAND industry is producing is actually doubling every 3 years. So this is in line with the data growth that I showed on the prior slide. Because the data growth is happening exponentially, this NAND sub-industry bits is also growing exponentially. Hence, that data can be stored in NAND flash bits. Now, you cannot have exponential growth in bits if the price of that thing does not fall, right? So you are a consumer, you buy laptops, you buy iPhones, or different types of memories. You might have noticed that the price of the card is not changing. If you go and buy a digital card today, it's still probably $20. If you go 10 years ago, it was still $20. But what has changed is the density, the capacity of the card has become 100x, 1000x. Used to be megabyte, then became gigabyte, now it's terabyte. But it's still $20. So that means that dollar per gigabyte, if you plot, it's actually exponentially going down. This is why the total amount of bit shipment can go up. Because if it required you the same amount of money to buy the same amount of bits, there's no way world can sustain this. It will cost you trillions of dollars to buy that much memory. The reason why the memory consumption has been increasing exponentially is because the selling price has been coming down exponentially. Both these things are interconnected. One cannot happen without the other. If this was not happening, this won't be happening. So really the key is this. This drives this. So the question is, how is this possible? How many things do you see in the world where the price drops 15% a year? Does it happen for a car? Does it happen for a house? Like, there are very, very few things where the price of that thing drops 15% a year. This only happens in consumer electronics. This is the power of semiconductor chips. This is the power of Moore's law scaling. And I'll talk about that next. So this is very unique to chip industry. This is not, don't take it as a granted. This requires massive innovation, massive talent, massive investment. Only then all this happens. This is not, doesn't happen randomly. So let's now talk about how did this happen, because this is the force that drives everything. Because price goes down, hence you can buy more memory, hence you can store the data into the memory. This is all interconnected. So how is this happening is the most important question to understand, and that's where technology development comes in. So how did we do this? How did we keep improving the cost per gigabyte exponentially reducing every year? Well, it's done through this. So it's fundamentally done through Moore's law. So what does Moore's law mean? Moore's law mean in a given area, I'm able to pack more and more information at an exponential pace. Almost every 3 year or every 1.5 year, I'm doubling the amount of information I'm packing or amount of transistors I'm packing in a certain area. That's what Moore's law means. So you can plot cost on the log scale, or you could plot density on log scale. All of them will look similar type of plots. So, but here we are plotting cost. So you can see what has been happening since 2001 all the way to 2023 now. So over the course of 20 years, the cost of 1 gigabyte of memory has dropped 1000x. 1000x, okay? There's not too many things in the world that have dropped cost 1000x in 20 years. This is the power of scaling, power of Moore's law. How has it happened? So it used to be 1 gigabyte in the same chip size. The chips is still looks like a penny basically, it's size of a penny. In the same chip, it used to be 1 gigabit before. Then it became 10 gigabit. Then it became 100 gigabit. Then it became 1 terabit. Nowadays, our latest chip that we produce is actually 1 terabit chip. It used to be 1 gigabit. That is 1000x right there. But the chip size has not changed, right? Your USB drive is still the same size. Your phone, the memory chip in it is still the same size. So what has happened is that it has become more and more dense. And as a result, the cost per gigabyte has exponentially dropped. So this has happened over 17 generations of 3D, 17 generation of NAND over 20-year period of time. So this is the power of Moore's law that exponentially drives the cost down, exponentially causes the density to go up, and as a result, you can exponentially store more and more data every generation, every year. So now, in order to understand this more in depth, that how did this happen? How did we achieve 1000x more density through technology innovation? We need to start with the basics of what a flash memory cell is. So some of you might have studied MOSFET. So MOSFET is basically a fixed threshold voltage device. What that means is you have a gate. So it's a 3-terminal device. You have a source, drain, and the current flows from source to drain. So like this, we call it channel. And then the amount of current that flows is dictated by the gate voltage. That's what a MOSFET is. So if I want to have high current flow, I'll increase the gate voltage. If I want a low current flow, I'll reduce the gate voltage. So, but the gate voltage at which the cell current goes from nearly zero to a high number is called the threshold voltage of that device. So a MOSFET is a fixed threshold voltage device. That means if you construct one transistor like this, it has one voltage at which it will turn on from off to on. It's a switch basically. You apply a voltage on it, it turns from off to on. By the way, does any of you know who invented MOSFET? Whoever answers the question is going to get a free USB drive. Yeah?
Muhammad Atala. He was an Egyptian Purdue.
That's right. That's right. So one USB drive coming your way.
Actually. Oh, thank you.
Yes. So it was actually, I hope you didn't tell him, right? There's some collusion going on or something. So yes, it was actually Muhammad Martin Atala. He was a co-inventor of MOSFET, and he did his graduate school in Purdue University. So you should all be proud to study in this great university, right? So yeah, he was education MSc and PhD in Purdue University. So he invented MOSFET along with another co-inventor he had. So MOSFET is a fixed threshold voltage device. Now MOSFET is not a memory, because a memory means that I put some information in it and I read it. It should be able to tell me is the information 0 or a 1, right? Any information can be represented in a form of 0 or a 1. So a memory means I program data into it and I come back to read it, and I read it exactly the same way. It should tell me is it a 0 or a 1. But in this device, there's nothing programmable. It's a fixed threshold voltage device. So no matter what I do, it basically, it cannot tell me what data is stored in it. So what we do is we take a MOSFET and we separate the gate out of it, and then we plug in a charge storage layer in there, and that's where the electrons are stored, and the amount of electrons that are stored here dictate whether it's a 0 or a 1. So if you want to store, if you want a 0, you will store more electrons in it by programming it to some high voltage. If you want it to be a 0, you will store less electrons in it. So depending on the program operation you did, you come back to read it, it will tell you whether the cell is 0 or a 1. Because if you have electrons stored in this area, it's going to basically reduce the amount of cell current that flows under it. So that will change the threshold voltage of the cell. So you have switched a fixed threshold voltage device to a variable threshold voltage device. And that's how a MOSFET can become a memory. So that's a very basic flash memory cell. And then this is how we do the flash memory cell operation by erase program read. So in order to erase the cell, what you do is you apply a high voltage. This is an erased cell as born. So there's no electrons in this. So now if you apply some gate voltage on it, let's say 0 volt, you'll see some high current in it. So now when you read back, you see high current. This is defined as a 1. Then if you want to switch it to a 0, what you do is you apply some high voltage on the gate, you inject some electrons into the charge storage area. Now these electrons start creating a shielding field, which actually reduces cell current flowing through this. So now when you come back to read the same cell with the same gate voltage applied, the cell current now is going to be almost 0. So basically the threshold voltage of the cell has shifted now from a low value to high value. And hence it's a memory now. Because now by changing the amount of electrons in there, I can modulate the threshold voltage of the cell. So you have shifted from, in this example, from 1 to a 0. And if you want to do erase, you just reverse the operation and you apply a voltage on the bottom and you inject the electrons out of the charge storage area, and now it becomes a 1 device. So this is how you can switch this memory from a 0 to a 1 by either programming or erasing. So that's how a MOSFET becomes a flash memory, by simply inserting this charge storage layer, which modulates the threshold voltage of the cell. So now, this was just one single cell, but now talking about, again, we are trying to answer the question, how do we make this memory more and more and more dense? How did it become 1000x cheaper, 1000x more dense? It happened because of scaling. So this one minimum unit, how big is this thing? That's what determines how many information can I pack in one area. Because in one area, if I have this much chip size, how much of these single cells I can store in it, that's what determines how much memory I'm storing in the chip. So that happens by the physical scaling of the cell. So the way, if you keep on reducing the dimension of the cell to a smaller and smaller number, then you keep on increasing the density of the chip. That's how Moore's law works. But obviously it's not as easy as it sounds, right? So what happens is that if you keep on making these dimensions smaller and smaller, the cross-coupling effects between them keep on getting stronger and stronger and stronger. So cross-coupling means I program this guy, and then I program this guy, and then the programming of this guy affects this guy. That's crosstalk. This is a challenge you have to deal with if you keep on scaling the device more and more physically. So that's what is plotted here, proximity effect, or you can call it like crosstalk effect. It almost exponentially goes up as you keep on scaling the device. So that's why you have to keep innovating to solve these problems. You can't just say, oh, all I did is scale and it will just work. No, it won't work because you have too much crosstalk and it will create too much errors between 1 and 0 state if you don't solve it. So how do you think you can reduce crosstalk? Crosstalk fundamentally comes from this coupling between two adjacent nodes. So coupling fundamentally is a function of how much capacitance exists between two different structures here. How do you think you can reduce the coupling? Anybody have any thoughts? What material can I use here to reduce the amount of coupling between these two things? Yeah, good.
Silicon.
What's that?
Silicon.
Silicon? Okay, silicon is one option. Is that the least way to reduce the capacitance? Could we use another material? Any other guesses? Yeah? Metallic. Metallic actually is the other way around. If something is metallic, it has strong coupling, because if I do something here, I'll immediately feed it on the other side. So think of something opposite of a metal. Yeah?
Ceramic or something? Something with very high insulation properties?
Yes. What has high insulation properties? Yes. Okay. Ceramic version 2. Yes.
Like some kind of like oxygen oxide, something like that.
What did you say?
Oxygen or something like that.
Oxygen. Do you guys know a double pane window? Right? Most of you probably have a double pane window in your house. Why is it double pane? It's also insulation. It's heat insulation. Here it's electrical insulation, almost the same thing. Why is it double pane? Yes? Go ahead. What's that?
It's a vacuum.
Vacuum. That's right. It's actually air in there. And it's actually lack of air, vacuum. So yeah, another USB going that way. Yes, so that's exactly what the industry did. So we created air gaps. Air gaps, because air has dielectric constant 1. That's the least insulation you can have, most insulation you can have. The higher the dielectric constant, the more coupling you will have. So by introducing air gap, you're able to reduce proximity effects like this, right? So that's one innovation industry came with, right? That's one way we mitigated scaling effects. Apart from this, there are some electrical, this is a physical innovation. You change something in the structure itself to improve something fundamentally. In addition to that, there are electrical innovations as well. Electrical innovations means you have the structure you have, how can I operate it to get the most out of it? That's an electrical innovation angle. So there are different program algorithms we have deployed, which is also a form of innovation. For example, doing two-pass programming. So the cross-coupling is a function of what is how many electrons you programmed in this guy after programming this guy. So instead of doing in one step, which is what we call single-pass programming, you program one cell, then you program the other cell right after that. What you can do is two-pass programming. You program in 2 stages. First, you program this guy to an intermediate state. Then you program this guy to an intermediate state. Then you come back to this guy and program it to the final pass. That's another way to reduce cross-coupling, because you reduce the swing from first pass to second pass. This is an electrical innovation. So innovation comes in different fronts. It could be physical ways to improve a problem, which is more fundamental, to be honest. You improve the physical process of manufacturing. Or you could change it electrically, which means how you operate the memory. That's another way to innovate. Both these things combined is how we are able to sustain this scaling. So you can see by innovating like this, we're able to control this exponentially growth of proximity effects. We're able to slow it down. And these are kind of innovations that are needed to keep this density growth happening at an exponential pace. So now I'll just near the end of my talk to talk about the future of the NAND flash going forward. So like I said, the proximity effects we have been dealing with by innovating through whether it's physical innovation, whether it's electrical innovation. But at some point it runs out of steam. There's only so much you can do. So we reached a point around what we call 1Z nanometer, which was 15 nanometer, where the proximity effects were just too high, and we didn't have too much left in the bag, right? So at that point, you have to completely think of a new architecture. At some point, you have to think like, okay, I cannot pack more cells here. What do I do? What do you think you will do? There you go. See, okay, another USB coming there. Yeah. So what's that? Yeah, you stack it. So you go 3D, basically, right? So this is all two-dimensional. We're trying to just pack things here. But guess what? There's another dimension that we have in our world, 3 dimensions. So can we stack multiple layers of this, right? So that's what the industry did. We took that two-dimensional cell, we flipped it vertically, and then we created multiple layers of it. So that's the so-called 3D NAND, which we internally call BICs. So now, instead of having one layer of memory cell, you have multiple layers of memory cell. And not only that, we created the memory cells now became cylindrical, which inherently reduces cross-coupling effects, because now there's very little, basically there's a lot less coupling effects between these two things, because the surround structure inherently is a lot more gate control as compared to this planar structure. So this is the new phenomena that happened in 3D in the industry back in 2016 or so. And guess what that did to proximity effects? Totally crashed it down, all the way down to like 10 years back. That's another innovation. That's another physical innovation. It's an architecture innovation. It's not just fine tweaking, let me change material here, material there. It totally changed the way the cell structure is. That's another innovation. And now we're in a journey again of slowly growing cross-coupling effects again, but we are significantly better than what we used to be before. So this is how the industry has been keep on innovating to keep up with these proximity effects, and that's what has been driving these moves to continue to happen. And now the number of layers have been keep on growing every generation. So Western Digital started manufacturing our second generation of 3D NAND, which was 48 layer. Then almost every 1.5 years, we've been coming up with the next generation. We went to 64 layer, 96, and now we're all the way up to 218 layer. And not only the layer count is higher, but there are other things also happening. So the other aspect is that we only talked about memory cell in this talk, but the other thing is how do you program these memory cells? How do you generate voltages to program and erase these memory cells? That is generated by CMOS circuits, like transistors. So where do you place the CMOS is another aspect of scaling. So up to this point, we were putting CMOS on side by side. Then from our 6th generation of 3D NAND, we started to put CMOS under the array. And finally, on our 8th generation of 3D NAND, big SATA as we call it, 218 layer, the CMOS actually is a separate wafer from the array wafer. These are two separate wafers bonded together. This is another architecture jump we have made in the NAND evolution. So, but it's not as easy as it sounds. It's not like, okay, let me just add more layer. There are many things that get worse if you add more layers. One of the big one is that the more layers you add, the taller the stack becomes, the longer the channel length becomes. So the cell current keeps getting lower and lower and lower because the resistivities keep on going up, the bigger the channel is, and that requires more innovation to tackle those problems. So the challenges are not over. We ultimately need talent, people like you, to keep solving these problems constantly. And one challenge we solve, then the other challenge comes in and keeps on doing that. This is what it takes to keep on innovating and keep on driving this insatiable need of data growth, right? So there's more layer increase going to come, but it will require constant innovation. Innovation is the way we survive, basically, not thrive. We survive through innovation. If you don't innovate, you die in this industry. So like I said, this is my last slide. So we have other ways of scaling 3D NAND too. Here we focused on layer growth and physical scaling, but which is the first one here, vertical scaling. It has its own challenges. But we also do scaling in other ways in 3D NAND. One is lateral scaling. That means in each layer, how many cells are we packing? That's one aspect of scaling. The other, what I just touched on, architecture scaling, where the CMOS circuits are placed. So this is CMOS, this is array. Earlier, we used to place CMOS right next to each other, like this, circuit next to array. Now, a lot of our competitors right now are using this technology, CUA, CMOS under array. So red is the array, white is the CMOS. And then we have moved to CBA, CMOS bonded to array, and then which means two separate wafers, CMOS wafer, array wafer bonded to each other. And now, sooner or later, we'll move to triple wafer bonding, where you have two arrays bonded to one CMOS, or these two CMOS bonded to one array. So these are another scaling vectors that you have, dimensional scaling that you have. The last one is logical scaling. We didn't touch too much in this talk today, but when we talk about memory cell, when I described zeros and ones, that was 1 bit. That one cell can store either a 0 or a 1. But in reality, the mainstream memory that you buy today is this thing, TLC, triple level cell. In one single memory cell, you're storing 3 bits. So, and sooner or later, industry will start to converge to QLC. That means you can store 4 bits in one cell, quad level cell. And then hopefully one day we'll reach penta level cell. So this is again exponentially growing problem. The amount of states you have to store are exponentially growing, hence the difficulty is exponentially growing as well. So there's another knob of scaling, logical scaling. And I think if you're interested, we can talk more about that separately. So there are multiple knobs of scaling. Each one of them have their own challenges. Each one of them require innovation. And that's where we need talent. That's where we need people like you to work. But like I said in the beginning of the talk, this is essential for human civilization to continue the way we are continuing. Because if data is going to grow, you have to store data somewhere. If you don't do this, that will require so much money that it won't happen basically. You need to do scaling to make things cheap enough so you can store the exponentially growing data into the memory. This is all interconnected. So innovation is a must-have for ultimately for human civilizations to continue the way it's continuing. Without that, something has to give basically. So that's why innovation is the way we survive here. And that's why flash memory has been innovating so far to keep up with world storage needs, but it's not guaranteed. And we have to keep working on it day to day, keep thinking of problems, keep solving those problems through innovation. That's how this industry works. Yeah. Okay, that's all I have.
Well, thank you, Devanshu, for the great talk. We have about 5 minutes or so for a few questions. If you guys just raise your hand, and please wait for Joey to come around to hand the microphone before you ask it. So you can go ahead and start up here.
So hi. First of all, thank you for coming. And so you kind of talked a lot about like how pretty much how each individual cell stores data. But what I want to know is, how is it that like you're able to, like, for example, like the little USBs that you're giving around, right? How is it that the USB is able to know like which cell it's like calling and making sure that it's like storing in the right cell and then retrieving from the right cell? I know that you briefly mentioned CMOS, but like how do you put it together pretty much?
Yeah, it's a good question. So in a SSD, so this talk mostly focused on the chip, the memory chip. But if you think from a product point of view, let's take an SSD or a USB. When you open it up, you have the flash memory chip in it, but you also have a controller chip or what's called ASIC. So ASIC kind of manages the NAND. So when you as a host say, hey, go program the data, you don't talk to the NAND directly. There's an ASIC is the middle guy in between. It's going to talk, ASIC is going to translate your language to NAND. It's going to manage where the data goes. So it manages the NAND. So ASIC decides where data goes and it remembers where data went. It stores what they call logical to physical pages. So it stores information, it remembers this data went here, and that's all managed through ASIC, through the controller chip. Yeah.
Okay, and then can I ask, just like, if you have like a lot of pieces of like CMOS, how are you able to know, like, how is the ASIC able to know, like, which one should it send a specific piece of like data to? And pretty much just making sure that like that process like coordinated, like how does that work?
Yeah, so this is a field of its own. Right, this goes into system engineering.
Yeah, definitely.
So it's like you can do a course on it. But basically, how do you manage data? How do you organize data? Right, the ASIC is like a brain, so it sort of manages where it goes
Okay, thank you.
Sure.
Hello, my name is Evan, and I was, if you could go back onto the last slide, I remember near the end there was like a logical scaling part, right? And you mentioned currently you guys are doing TOC. I know this is kind of a silly question, but why aren't QOC and POC currently possible?
Yeah. Does
I
this
know all the
picture tell
experts
you
in the room are
something?
going to laugh at me right now, but I was wondering why aren't QOC and POC currently possible?
Look at the picture. Doesn't it look like things are getting harder on the right side? It's getting crowded. So look, the thing is, in order for you to separate a 0 from a 1, you need these states to have some gap in between. Okay? Because that's differentiate. Because when you read the cell, I'm going to read right in between, and I want to make sure that there is no overlap between the states. So as you keep on trying to store more and more states, you can see the gap is reducing. The more states you store, the more overlap you get. Every overlap is an error of the chip. So the more states you want to store, the more the errors will be, and that's where the challenge is. The second thing is that it takes time to program all these states. So each of these states requires a lot of programming. So the more states you have, the more time it takes to program, so slower the device becomes. So there are two challenges. As you go in this direction, it's getting slower and slower and getting less reliable. So you have to manage those challenges to make it good enough for you to sell that product. So it's basically degradation of reliability and performance. That's what limits our ability to go into that direction. Yeah. So today, mainstream is this. I would say 90% of bits you buy in the market are TLC, 10% on QLC. PLC is nearly zero. But over time, I think it's going to migrate more and more in this direction because of cost. Yeah. It's cheaper to make QLC as compared to TLC. Yeah.
I think a question over there.
My question isn't related to technology per se, but more towards the market side.
Yep.
With like flash memory reaching so high limits, with like basically us having 10, 20 terabyte flash storages, do you think there's a market where hard drives are kind of phased out in the server side, or is there still like demand for hard drives being used?
Yeah, there's still a huge demand of hard drive being used, mainly because of price. So hard drives are still cheap. So when you look at data center, not all storage requires performance. So flash is good in performance, like I was showing in the memory hierarchy. Flash is almost 10x or 100x faster than hard disk drive. But it is also 4x to 5x more expensive, right? So if you want performance, you will buy flash. So when you look at your cloud, if you use Facebook, try going to your 10-year-old picture and see how long it takes to load it. It's pretty slow. Try going to the picture that you uploaded on yesterday. It's pretty fast. You know what's happening, what they're doing? They're storing your old pictures into the hard disk or possibly even lower drives than that, like optical drives. They're storing your recent pictures into flash drive. So all these companies optimize their system to get the best possible cost and performance. So that's why hard disk still has a long way to go before it's eliminated. But in consumer market, durability matters. You want to be able to throw your laptop around, it should not break. That's why flash is rules in consumer market, but in data center, nobody's throwing the server away, right? So durability is not so important in the data center. That's why hard disk still rules data center. Will continue to rule for next 10 years at least.